Welcome back, everyone. Today's explainer is brought to you by Forge College. And man, am I excited for this one. We are finally getting our hands dirty. Throughout this capstone module for events and logging in Solidity, we spent a lot of time talking about design. But today we are actually wiring up our smart contract assembly line. Our main goal here is to implement event-driven logic directly into our contract functions. We want to make absolutely sure that our on-chain actions produce perfectly reliable off-chain logs. So let's dive right in.
Here's our quick roadmap for today. We'll start by moving from blueprint to implementation, then tackle creating the record state and updating with snapshots. After that, we'll cover finalizing and timestamps, verifying the logs, and wrap up with our conclusion and next steps.
Okay. Part 1. Blueprint to implementation. Time to wire the machine.
So in our previous lesson, we were acting as architects, right? Drafting out our event blueprints. But now, to wire them up correctly, we have to grasp one foundational concept, and that is deterministic ordering. This is literally the bedrock of reliable smart contract integration. It's the ironclad guarantee that your emitted logs perfectly, and I mean perfectly, reflect the final state changes of your contract in a totally predictable sequence. Think about it. If an off-chain listener sees an event, they need to be absolutely certain the contract storage matches it at that exact block. Because without this guarantee, your monitoring tool is basically just guessing, and we definitely don't want that.
To really show why this ordering matters so much, let's look at the wrong way first, which is emitting the event before you actually change the state. It's kind of like sending out change of address cards to all your friends and family before you've actually signed the lease on your new apartment. If that lease falls through, you have just created a massive, confusing mess for everyone. In Solidity, emitting early is just a recipe for time-traveling data bugs. The right way? You change the state first, lock it in securely, and only then do you emit the event.
Moving right along to Part 2, creating the record state, the first component.
All right, keeping that golden rule in mind, let's fire up the assembly line. The real magic in our schematic is the exact sequential logic we use to build a new component from scratch. Step 1, we compute the new identifier, basically grabbing the next available ID. Step 2, we write that new record data directly to our contract storage mapping. Boom, the on-chain state is now strictly updated. And finally, Step 3, only after that state is securely saved to storage do we actually emit the record-created event. By strictly sticking to this 1, 2, 3 sequence, any event watcher that inspects the contract storage after seeing our log is going to observe a perfectly consistent state. No surprises.
Next up, Part 3. Updating with snapshots, modifying the machine.
So, now that we know how to create components, modifying them on our assembly line requires some really careful handling of data. And this brings us to a super fun chronological puzzle. How exactly do we log the past and the future at the exact same time? Think about it. If our event needs to tell external listeners what the data was and what it is now, but we can only emit the event after the state is changed, well, aren't we kind of stuck? Because once we overwrite that state, the past is gone forever, right? Well, not if we use snapshotting. Inside our update function, we first read the current state, and of course, validate the owner. Then, and here's the trick, before we change anything at all, we take a snapshot. We save the old metadata into a temporary local memory variable, which we'll call old meta. Next, we safely mutate the contract storage over to the new meta. Finally, we emit our record updated event, passing in both our saved old meta and our freshly written new meta. This is a really clever technical move because it completely saves our monitoring tools from having to do those expensive, complex historical state reads. We're essentially handing them the exact delta on a silver platter.
That brings us to Part 4, finalizing and timestamps, where we talk about retiring the component.
Okay, so our component has been created and updated. Let's officially decommission it. The sequence here is just as strict as before. First, we validate ownership and make sure the record isn't already finalized. Second, we apply the actual state mutation by flipping our finalized Boolean flag to true. Third, we capture the exact time using block.timestamp. And fourth, we emit the record finalized event. Notice a pattern here? We emit only after the Boolean flag is flipped. This perfectly aligns with Solidity's famous checks, effects, interactions pattern. We checked our conditions, we affected our state change, and then, finally, we interacted with the outside world.
Let's move to Part 5, verifying the logs, quality assurance.
So we've built the machine, right? But nobody wants to ship an expensive, hard-coded bug. We need to run a test.
When we execute a local test script going through the whole process of creating, updating, and finalizing a record, we can capture the transaction logs and compare them against our engineering ledger. What we really want to confirm here is that our stable identifiers, things like the owner and the ID, are properly sitting as searchable indexed fields. Meanwhile, our larger, more volatile payloads, like the metadata and timestamps, are kept snugly over in the non-indexed data side, and we do that to save us precious gas.
So what exactly does a successful QA check look like? Well, it really boils down to 3 critical parameters. First, the event parameter order in your logs absolutely must match the specification document you wrote up in the design phase. Second, you have to verify that your indexed fields are strictly stable identifiers. Seriously, no massive data blobs where they don't belong. And third, if you query the contract at the exact block the event fired, the storage state has to perfectly match the emitted log. If you can pass these 3 checks, you're guaranteeing a consistent, totally stress-free implementation for anyone who might be listening to your contract.
And finally, Part 6, Conclusion and Next Steps, Preparing for Observability.
We have officially gone from a theoretical design to a fully assembled smart contract. Now, if you take only one single thing away from this entire explainer, please let it be this: emit after committed state changes. It really isn't just a suggestion. You should treat it as an unbreakable law of physics when you're building reliable integrations. Mutating your state before emitting preserves determinism, it drastically reduces ambiguity, and it ensures that the off-chain world stays perfectly synchronized with your on-chain reality.
Which leaves us with one final, kind of provocative question. Now that your smart contract is perfectly wired up and blasting out these pristine logs, are your external listeners actually ready to handle the data it unleashes? Well, in our next lesson, we're going to dive deep into the validation and observability of emitted events, and we'll simulate some real-world consumers to see if our system really holds up under pressure. Until then, thank you so much for hanging out with me. This explainer was made by Forge College. Be sure to check out our website at Forge College to dive deeper into this subject and to explore a ton of other amazing Web3 topics. Happy coding, and I'll see you in the next one.